Welcome everyone to the class. So last time we looked at a fully connected neural network or a multi-layer perceptron, and we also looked at how to conduct empirical risk minimization on such an architecture using gradient descent. Specifically, we walked through the error back propagation algorithm, which is a repeated application of chain rule to find the gradients of an architecture which is called neural networks. That is what we saw the last time. In this class, we will look at a few improvisations over the multi-layer perceptron. Okay, I told you the last class that the choice of the function h theta that we make is also called as an architecture in the neural network community. So we will look at a few architectural changes for neural networks. So specifically, I'll talk about three broad classes of architectures. One is the convolutional neural networks or CNNs. The other is the recurrent neural networks, of which gated recurrent units and LSTMs are members. And then we'll also look at transformers as which is the state of the art architecture that is used in modern day machine learning applications. Okay, so let us start with convolutional neural networks or CNNs. Before we go on to the specific of this architecture, right, I wanted to make a few observations which are applicable across different architectures of neural networks or general observations. For one, universal approximation theorem already tells us that all we need is a neural network, a two-layer neural network with a single hidden layer to approximate any function to arbitrary closeness. So, theoretically speaking, all problems in machine learning can be solved using a single hidden layer neural network, right? So then why do you need deeper neural networks? We saw the argument the last time. It is mostly for computational convenience and also better convergence. So this is universal approximation theorem is a theoretical result. Empirically, when you are solving ERM on these kinds of architectures, the kind of functional choices that we make for h theta matters. How? You see that ERM is an optimization problem over the loss landscape or the empirical risk landscape, and the number of parameters that we have is typically very high, right, of order of tens and hundreds and thousands or even billions these days. So in such high dimensional spaces, when you are sampling, when you are searching using, so let's say that you have two choices, one to search over one class of functions and the other is to search over the other class of functions which would approximate the same objective function. The choice of search space that you make, okay, has a considerable impact on what point on the loss landscape or the objective function landscape that the optimization algorithm take you to. Does it make sense? Theoretically speaking, a single hidden layer neural network can take you there, wherever the optimal point is. But if you restrict, see, you can see that, right? Any kind of restriction that we do or an architectural choice that we do is actually restricting the search space in the space of all continuous functions. So you are saying amongst all possible continuous functions that I can choose from, I will search only within a small subspace of this space of continuous functions. So every subspace becomes a particular architecture. So what people have found out is that if you make particular choices of the class of functions that we are looking at for certain kinds of problems, okay, ERM would be feasible with certain kinds of architectures, or rather this feasibility can come in terms of faster convergence or better accuracy and so on. So there have been a lot of studies that would show that whatever you can do with a CNN can be done using a multi-layer perceptron. Just that you need a lot more training and more careful choices of hyperparameters and so on. Okay, so whatever architecture we see is a choice that is made to ensure that practically when we conduct ERM on these kinds of function spaces, they would better converge on the particular kind of problems that we are looking at. So this is the general observation. So the idea, the point is that while our choice of architectures make practical sense, theoretically speaking, they do not give you any more guarantees of convergence than a single hidden layer neural network or an MLP. So you should remember this. Okay. Having said that, as I said, practically speaking, making certain choices on the architecture or the function spaces that you are searching on can lead to better convergence and accuracy and so on. So therefore, it becomes important to look at those meaningful choices that we make, okay, on the architectures for certain kinds of problems. Okay. Now that's point number one. Point number two that I wanted to make is that any kind of architectural choice that we make or some restriction that we put on the function space is equivalent to choosing a prior on our parameters. So why is that the case? I'll show you examples when we go to these architectures, but broadly speaking, here is the point. So what is an architectural tweak that we make? The raw vanilla architecture is that of MLP. Okay, it's a multi-layer perceptron where every neuron is connected to every other neuron in all layers. Now let's say that I make I make a choice saying that the weights connecting neuron 15 to neuron 16, okay, should always be 0. You understand what I am saying? Some take two arbitrary neurons and say that there should not be a connection between these two. What is that I am doing? If you think about it, I am imposing a Dirac delta prior on that particular parameter in the parameter space, saying with probability 1, choose this particular weight to be 0 or whatever value. You see what I am saying? So you can see all tweaks that I make on a vanilla MLP in terms of parameters as a Bayesian prior that I am putting on the parameter space. So that way a CNN is a regularized multi-layer perceptron. We will see how exactly it is done. A CNN is a regularized MLP and an RNN is a regularized MLP, and so is a transformer. So any kind of, so you take the most general function and start saying that okay, this parameter can take only this value with a certain probability, this parameter can take this value with certain probability and so on. That becomes a new architecture which is nothing but imposing Bayesian priors on MLP. So that's why remember when we discuss regularization, I told you that one other way to regularize is to make architectural choices. Okay, that is why CNN, all architectural choices that we make can be seen as regularizers. Now, why are regularizers important? We know that for particular type of problems that we choose, if I know how the parameters are going to be, then it's a better idea to impose that on your modeling choice so that ERM becomes easier. We know why we impose bias on our models, right? That's exactly why. And we also know that if you have infinite data, then having a bias does not matter because maximum likelihood estimate also converges to the true estimate of the parameter as well. So this is I wanted to, I just spent 5-10 minutes on this topic because whenever you see an architectural choice that is being made, you should always see that as a choice of regularizers that we are making on the function spaces so that it chooses it converges. Whatever properties that are desired are imposed on the particular function spaces. Okay, is that all right? Okay, so with that, let us look at convolutional neural networks. So these are I'll actually write this as regularized MLP suited for grid like topologies. Now, if I have data that is grid like, so what do I mean by grid? Its image is an example. So you can arrange your data semantically in like a grid, a tensor basically. So see, one can argue that even a vector is grid, right? Because it is a one-dimensional tensor that way. I agree with you. So that's why you have a 1D CNN. But to start with, the motivation comes from the fact that if you have grid-like topology, of which image is an example, right? Then you have to have certain regularizers on MLP, and if you do that, then what the architecture that you get is a convolutional neural network. Okay. Now, example it's an image, and have 3D volumes. And so on. So these are grid-like topology, right? This can come in multiple applications. Now, can't we use an MLP on image? We can definitely use an MLP on image, right? But treating that as a vector. But as I said, this is a specific regularizer which is custom made for these kinds of data. Okay. So now what's CNN, right? So CNNs, so it's an MLP with two specific regularizers. I'll say hard regularizers on, I'll tell you what that means, on the parameter space. So one, the idea is local receptive field, it's called local receptive field. There is one type of regularization that is done, the other type is parameter sharing. Across topology. So these are the two ideas, these are the two regularizers that are put on MLP, and if you do that, the kind of architecture that you get is called a convolutional neural network. I will tell you why it is called a CNN as well. Okay. So what are these things? Let us look at this. So let us say that we have data in RD for now, and we still have a vector kind of topology. We still don't have this grid kind of data right now, but this is for understanding sake. X is in RD. So we have d dimensions of data, and then let us say that we have neurons. So this is an MLP. So typically what happens in an MLP is that every dimension of data is connected to every neuron, correct? So connect this, all dimensions of data to this neuron, right? And this neuron is also connected to all data dimensions and so on, right? And this happens subsequently with all neurons, you know that, right? So suppose I tell you this, that I don't connect all data dimensions to a particular neuron, but I only connect a subset of all data dimensions to a particular neuron. Does it make sense? So this is an architectural choice that I am making. So why am I making this? I will tell you in a while. Right? There is some intuition that is given, which I'll talk about. But did you understand what is it? Instead of connecting all data dimensions to every neuron, I will only connect a subset of data dimensions to every neuron. In each layer, to every neuron, in each layer, to every neuron, I only connect a subset of data, and this subset, right, is a hyperparameter. So what I do is, instead of connecting this, I only connect these 4 data dimensions to first neuron, and the second 4 dimensions to the second neuron, and third set of 4 dimensions to third neuron, and so on. And I do the same thing in the next layer as well, right? So these 2 are connected to this, and then these 2 are connected to this, and so on. Do you see this idea? So this thing is exactly what is called as local receptive field. So just a second. Yes. Connect only a subset of data or activations, depending upon what layer are you in, to every neuron in each layer. And by the way, a neuron, so we all know what a neuron is, right? It's that W transpose X operation that we do is what is referred to as neuron. So now every neuron has this thing called receptive field. So what is receptive field? Receptive field is simply the data dimensions or the activation dimensions that are connected to this particular neuron from the previous layer. That is called receptive field of a neuron, for obvious reasons, right? Yeah, so there is a neuron and it is looking at whatever activations or data in the previous layer is called the receptive field of that particular neuron. Now what you are doing is, you are making the receptive field to be local. Instead of making it a neuron with a global receptive field, you are making it local receptive field. Is that idea clear? Any questions on this? So now how many neurons do we connect to the next neuron is a hyperparameter, and will there be an overlap? Not non-overlap is also a hyperparameter, as we will see now. It's called stride in the CNN language. We will talk about it in a while, right? But the idea is to only select a subset of the previous layer's neuron and connect it to the next layer. So that's the idea of local receptive field. Any questions?
Receptive field, that is like if I am suppose in the second last layer and I connect two neurons to the last layer, so receptive field would be like two layer like these two things or the like input how many data points of the input.
That's a nomenclature question. Typically what happens is for a given neuron, you only look at the most previous layer and then talk of receptive field. That's just a language, right? So yeah.
Can there be any neuron empty in any layer?
Question is, can there be any neuron that is not connected to anything? No.
Connected to in the upper layer as well as the lower layer.
So
Should have at least one connection.
come again?
It should have at least one connection.
No, always in the immediate next layer. Till we talk about something called skip connections, which we will do in a while. Yeah. What is random here? Subset is a hyperparameter, meaning you select which subset you will have to connect to. But once you do that, it's there's an algorithm to determine. Meaning, you do it in a systematic way. Yeah, it's not random. Yeah. Is it okay? Yeah. See, now you can see this, right? So what am I actually doing is, if you look at the weights, as I said, no, W1, W2 up to WP, if there are P number of neurons here, if I draw a distribution of WP, right, or distribution of all parameters in the WP space, by doing this, what am I doing? I'm choosing a particular distribution where I'm saying that 4 dimensions of this W can take any values, but all the other dimensions have to be 0. So the likelihood or the probability of P minus 4 dimensions, okay, taking any value other than 0 is 0, or with probability 1 these things will take a value of 0. So that's why you see this as a very hard and strong regularizer, where you are saying, see, in most of the Bayesian regularization case, what do? We allow all values for the parameters with certain probabilities depending upon the strength of the regularizer. Here we are not even, allowing the value of some of the parameters to take any other value than 0. So probabilistically speaking, we are saying that we are putting a hard regularizer by saying that the probability of a few weights taking any other value than 0 is 0. You see that? It's actually a regularizer. Okay. So this is one idea. The other idea that is imposed on a CNN, as I said, is parameter sharing. Okay, I should tell you what is the, and by the way, this guy Jan LeCun who proposed this idea out of CNN, the intuition that is given behind putting this kind of a regularizer. You know that all regularizers are man-made in the sense that that's a design choice that we make. So why was this design choice made is that in an image, okay, the kind of features that we look at are mostly local in nature. What do you mean by that? So let's say that we have a picture of a home, whatever, right? Oh, just went away. Okay, so let's write it. See, typically in classical image processing, the problem is that you give an image and you try to make sense of it. Ultimate problem of computer vision or image processing is that you are given an image, you understand what the scene is. Or you say that, oh, here is a home, here is a person, here is this object, that object, and so on, and delineate. That's what human eyes do, isn't it? Now, to solve that problem, which is a very high level semantic problem, what people used to do in the image processing community classically is to break down the problem into pieces and say that let's start from identifying primitive features, like let's identify edges, okay, then let's identify lines, then let's identify complex pictures like triangles and regular polygons, and then try to hierarchically increase our understanding of the image and to finally to come to a particular conclusion, right. That's why there are lots of algorithms in image processing just to detect these primitive features such as edges, right, and contours and corners and so on, right. So now the assumption is that these kinds of features or these kinds of building blocks for semantic construction generally appear within subsets of data dimensions. But if you look at images, they are only, the edge is only here. The entire image is not an edge. If you want to look at an edge, you only look at one part of the image and so on. So if this neuron is supposed to fire, what do you mean by firing? W transpose X for that particular thing is greater than a particular threshold. We know that every perceptron can fire, right? So if this neuron has to fire for a particular feature, then it better only look at a small subset of data, so that what feature that it is looking at is locally restricted that way. So that's the intuition that is given for this. Make sense? And now what happens is, as somebody was asking, as you move deeper and deeper into the neural network, right, the receptive field of the neurons in the deeper layers actually keeps increasing, isn't it? Because this has a local receptive field and the neuron in the next layer has a local receptive field, but both the neurons at the previous layer has a larger receptive field and so on. Now what happens is, as you move deeper and deeper into the network, the hope is that these neurons will fire for more complex and hierarchical entities, semantic entities. That has been observed as well empirically, that the initial layers in a CNN fire for primitive features such as edges, lines, colors and so on. As you go deeper and deeper, they fire only for semantics, objects, is what has been observed. That's where it is coming from, right. So people try to mimic those kinds of things in an NLP. Now I'm repeating it because I'm not a neuroscientist, I'm an engineer, so and a bit of mathematician. So as far as the function approximation is concerned, all you need is an MLP. But if you put these kinds of regularizers, people have seen that the empirically they yield better results. Okay.
When we go layer wise, what guarantees the hierarchy to be built?
There is absolutely no guarantee.
And in a given layer, what guarantees like different features to be?
Even that is not guaranteed. Okay, the questions are like, what is the guarantee that hierarchical features are learned in an MLP? There is no guarantee, right? What is the guarantee that different neurons in a layer learns different features? There is no guarantee. Okay.
So this the way we have arranged our data, like different values, different pixels. Locally, if we are doing this, will be only getting associated with a subset of lines or pixels in one column or rows. And even then, it will not be able to. That local thing will have to be spherical. That is what I'm trying to like to get an edge or a corner.
Hold on to that question. I understand what you're asking. Just 5 minutes, it will be answered. Yeah.
How one neuron decides to extract or take some subsets of data points, like how the sensitivity is being decided by one connection with one data.
I didn't quite get the question. Is the question, how do you decide what subset of data is to be connected to what neuron? That's a hyperparameter I told you. That's a design choice. As a designer, you instruct the neural network to look at this particular subset. Okay. Your question will be answered in a while. Just hold on. Okay. This is about local receptive field, and the second kind of regularizer that we impose is what is called as parameter sharing, as I said. So what is this idea? Idea is, let's redraw this diagram. Okay, let me do it again. We have d dimensions of data, and we have neurons being connected here. Now the first kind of regularizer that we impose is that only a subset of these neurons are connected to everyone, right? Now if you go back to the intuition which led us to choose only a subset, what was the intuition? We said that features that occur in the images or any data are locally restricted, and that's why we want to look at only a few set of data dimensions. Now, suppose you are designing a neuron, or you are expecting a neuron to extract or fire for a particular feature. Let's say that it's an edge. So this edge, okay, has to be detected irrespective of where it occurs in an image. An edge detector has to be an edge detector no matter where this edge occurs in an image. Make sense? So suppose this yellow weights that we have, no, not yellow, what is this color? Orange. Yeah, did I become color blind? So this orange neurons or orange weights that we have connected is doing edge detection. Now don't ask me how do you know whether it's doing edge detection. I'm just giving you an example. It does something, okay, and let's say that it is for edge detection. Now this edge has to be detected no matter where it occurs in the data. Now how do you ensure that through a regularization here? By making that all the neurons in the first layer, right, are connected with the exact same weights. So what I do is I take this orange and connect all these neurons, okay, with the exact same weights.
Only a subset of data points.
Always, because the idea of local receptive field still exists, right, but I connect multiple subsets of data using the same set of weights to different neurons. So basically what I am saying is detect edge irrespective of where it occurs in the image. Does it make sense? So this is, let's say this is W1, W2, W3 and W4. This will still be W1, W2, W3 and W4. Now from a probabilistic standpoint, what am I doing? See, I said that in let's say 100 dimensional weight space, I am saying but for 4 weights, 96 of them are 0. So that's one regularizer I am putting, okay. Even I am putting another regularizer where I am saying that okay, these 4 of them, right, the next 4 of them also should have this exact same value with probability 1. That is the other regularizer I am saying, okay. So this idea is what is called as parameter sharing. So this is
And it goes on in all layers.
just a second. Yeah, questions here?
Does it go on in all layers?
Yeah, see, this happens everywhere. So now again here, if I connect this with green, this I will connect with the same green. This is theta 1, theta 2, this is again theta 1, theta 2 and so on. The idea of parameter sharing is there across the layers. Of course, I mean that's what we learn using ERM.
So in the first line itself, if you change W's to thetas, they directly detect like that only.
See, you are not fixing these W's, mind you. You are just doing this connection and still doing an ERM. Nobody is fixing these W's and thetas. They are learned through ERM.
So then this expressivity of this neural network will
Be restricted, right? The question is, won't the expressivity of this neural network get restricted? Well, there is one other layer to it that I will talk about. I mean, not layer in the sense of neural network. There is one other layer to it, or rather, one other dimension to it that I will talk. See, all these terms are mathematically well defined, right? One other aspect to it, right? Which I will talk about in a while. That will answer your question. Both of your questions will be answered at once, right? Are we doing disservice to the topology, and isn't it restrictive is something. And by the way, there is a universal approximation theorem for CNN as well. Okay, so that way it does not restrict the expressivity. But I mean, I was anyway asking the question myself. If we do this, then aren't we saying that all the neurons in a particular layer are only looking at one particular feature? That is a valid question, which I will answer in a while. Okay, but did you understand the idea of parameter sharing is all I wanted to ask you. No, it is like if you want to, if you are looking at detection of a particular feature, then this feature has to be detected no matter where it occurs in data. So this is what you are doing, right? Anyway, you are connecting a subset of data to a particular neuron. Now this neuron can detect an edge that appears only in 4 dimensions of data. Now suppose this particular feature appears in the fifth set of 4 data dimensions, then it has to detect the exact same edge irrespective of where it appears. Now if you look at this home image that I drew, let's say that this is an edge detector, an edge is here, 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 right? And it has to detect at all points. So that's why I need to have the exact same parameter across different data dimensions. All of them are connected to a local subset of data.
So, for example, if there is an edge at somewhere, then the first neuron in the second layer, in the first layer, if it detects an edge, then if there is an edge in another location, then the second neuron will detect it.
Exactly. So depending upon which neurons receptive field that particular edge falls into.
It's called retinotopy.
See, we have a neuroscientist in the class. There's a name for it. It's called retinotopy, is what he's saying. Yeah. So I mean, I don't know. That's not my statement, but yeah. So you can contact. Yeah.
So how the weights being updated? I did not understand that.
ERM, same thing. So you just restrict the architecture. You still do backprop. I'll write the equations in a while. Right? You still do the ERM. So this is a neural network. No, this is H theta. You still have the labels. You still have the H theta. You still have labels. Still have ERM. Do backprop and get it. That's it. Nothing changes. Yeah.
So what I was asking is, when the weights are all same, right? It's essentially, can you compare it to like a filter?
Good observation. I mean, maybe he's coming from the classical signal processing background. The question that he's asking is, if weights are same, isn't it the filter that is there in absolutely correct?
Another thing is,
It's a 2-dimension. Yeah, right now it looks like a 1-dimension filter. I'll show you how it can be represented as a grid in a while.
the other thing is it's partially answered because it's essentially just an edge detector when all the perceptrons have the same weights.
Yeah. So now, correct. That's correct. See, because you made that statement, I'll tell you a short anecdote. See, in classical image processing, what people were doing were coming up with these W's, okay, to do a particular function. For instance, there are a lot of edge detectors. So there's one example is this Gabor filter, right? The canny edge detector and so on. They are nothing but 10 numbers or 9 numbers in a grid. And you need to do that W transpose X operation. Now people spend their life in coming up with those 9 numbers so that a particular function happens. Now neural network comes and says, okay, everything can be learned. Told you in the first class, remember, ignorance modeling, right? So you let your neural network model whatever it wants. So you are exactly correct. This is actually a filter, a learnable filter.
So if your final classification problem or whatever depends only on edges, then this will work.
Not necessarily. I told you, right? Hierarchy, you have depth. So in second layer, it's not an edge. It may be something else. You're combining edge information to do something. And by the way, most of the times it is not even interpretable. See, there are techniques like GradCam and so on, where you can see what this neuron is firing for, right? But all those are empirical. You don't know what a neuron is doing, and that's the interpretation problem. And there are a few methods to do that, but exactly what this neuron is looking at, it's very hard to know that. Yeah, mathematically speaking, as I said, right? I mean, for us, it's an MLP with strong regularizers. That's it, and then we do ERM. That's all we care. But of course, these interpretations are pretty valid. So this is a filter, and it is a filter with learnable weights and so on. Any other question?
When we do backdrop, that would be we want these theta 1, theta 2 to remain same while the entire training. When we do backdrop, does that ensure that these because these get updated independently?
Okay, good question. The question is, how do we do backprop for this? Right, we'll have to ensure that these regularizers are imposed when you are doing backprop, right? Take it as a homework. I mean, you can do it. The way to do it is when we define that delta, right, where we have that error functions, the forward and the backward processes that we define, right, we'll have to ensure that the summations are done only over that, and yeah, only over a few subset, okay? And then when you are updating, you'll have to update in such a way that if you are doing it for one subset, the other subset to which these filters are connected are not updated. It's hard coded. maybe in tutorial. Yeah, see, that was another point that I wanted to make. I thought I would make it later. Every regularizer that you put on, architectural regularizer that you put on MLP will change the forward and reverse equations, no? We'll have to ensure that those those regularizers hard coded. And by the way, you should notice one other thing. These are hard regularizers, in the sense that these are hard coding that you do. Okay, there are some soft architectural level regularizers as well that I'll talk about. There is something called dropout. Okay, we'll talk about it in a while. But yeah, so as far as these hard regularizers are concerned, how do you impose them mathematically is by changing the forward and the backward. If you change the forward equations, the backward equations also will change, right? So you'll have to ensure that those things are taken care when you are doing backprop for a CNN. Yeah, that's how you implement it, by the way. Anyway, I would have told you later. Anything else? So you understood these two things, right? These are two major regularizers that are put on MLP to change it to a CNN, right? Local receptive field and parameter sharing. Okay. We will stop here and continue in the next lecture.